In this video, we're going to look at heat exchangers. And the way I usually like to set up heat exchangers is to call one of the fluids a cold fluid and one the hot fluid. So let's maybe start up here. So suppose we have like a hot fluid going in. And again, I'll just call it hot going in here. And then call it hot out here. And we're going to need a couple things from this. For the hot fluid, we're going to need its flow rate. And I'll call this M dot H for hot. And we're going to need the enthalpy. And we need the enthalpy going in. So call that H sub H dot I for in. And again, the M dot's going to be the same going in and going out. So we really don't need to put that M dot hot over here. But we are going to need the enthalpy, of course, will be different for the fluid leaving, like that. And this is going to be the cold fluid. And it's going to be like the M dot C like this. And for the inlet, we're also going to need HCI. That'd be the cold fluid at the inlet. And then for the cold fluid for the outlet, we're also going to need the enthalpy there. Again, the mass flow rate is going to be the same. MC out. Excuse me, HC out. So we need the flow rate of the hot fluid, the flow rate of the cold fluid. Again, the mass flow rate is going to be the same for in and out here, same for in and out here. Then we're going to need the enthalpy for the hot fluid in, enthalpy for the hot fluid out, enthalpy for the cold fluid in, enthalpy for the cold fluid out, like this. And we're going to assume there's no change in kinetic energy, no change in potential energy. So when we write down the first law, we can assume if we're summing up all the inlets and all the exits, and if we assume no change in potential and kinetic energy, these terms go away. And then also we're assuming that the heat exchanger is going to be insulated from the outside world. So that means our Q dot is going to be 0. There's no work done. And so over here, if we sum all the inlets, that's going to end up being like over here. This would be like, say, M dot H times the inlet up here, HHI. Then for the cold, we're going to have M dot C HCI for all the inlets. Then for the outlets, we'll subtract those. And the outlet's going to be here, M dot H H H O. And the outlet here is going to be M dot C times HCO like this. And now if we subtract these, and actually what I'm going to do, I'm going to kind of bring them over to the other side. And so that we'll end up with these two terms being positive and these two terms being negative. And then we'll put this term and this term together, and then this term and this term together. So we'll end up with M hot, let's say, times H out minus H in plus M dot C C out minus C in, set it equal to 0, like this. So this is the main equation we have to keep in mind when we work with heat exchangers. You have your mass flow rate of your hot times the enthalpy of the hot out minus enthalpy of the hot in plus the mass flow rate of the cold times the enthalpy of the cold out minus the enthalpy of the cold in. So we'll be using this quite a bit. And so keep this in mind and keep this picture in mind when you're doing these heat exchanger problems. So let's take a look at this problem. Saturated liquid water enters a heat exchanger at 20 psi with a flow rate of 50 pounds per minute, and it exits as a saturated liquid. The steam is to be cooled by water at 70 degrees Fahrenheit. The exit water temperature is not to exceed 77 degrees Fahrenheit. What water flow rate is required? So again, it's really asking what water flow rate is required to turn the saturated vapor to saturated liquid without the temperature of the water rising more than 7 degrees Fahrenheit. So let's take a look at that. So I made a little diagram here. So this is saturated vapor entering and saturated liquid exiting. It's a 20 psi. That's going to be our hot fluid. And 50 pounds per minute is the flow rate. And the cold fluid is the water. It's going to be entering at 70 degrees. And it's exiting again as water at 77 degrees. And as you're solving the problem, keep this in mind. You have the mass flow rate of the hot fluid times the enthalpy of the hot fluid out minus the enthalpy of the hot fluid in plus the mass flow rate of the cold fluid times the enthalpy of the cold fluid out minus the enthalpy of the cold fluid in, like this. And so keep that in mind as you're setting up this problem. And as before, what we usually want to do, we'll have maybe a couple of columns. We'll have like the hot fluid, and then over here maybe the cold fluid. And now for the cold fluid, it's water, so it's a little bit simpler to set this up. But for the hot fluid, we should probably put an inlet, and we'll also put an outlet for that. So for the inlet, it's coming in at 20 psi, and it's a saturated vapor. And then we have an outlet, so it's also going to be 20 psi, and it's saturated liquid. And so we can look up our values in the table. And so if we look under the saturated steam table, again, keeping this equation in mind, you see what we need. We need the enthalpies. So for the inlet of the hot fluid, again, that's going to be saturated vapor. So at 20 psi, again, remember, saturated vapor is going to be Hg. That's 1156.4. That's going to be the H hot in, which is going to be Hg. And again, let's double check. It's 1156.4. And that's going to be BTUs per pound. And then for the outlet, that's going to be HHO for the hot fluid out. And we know that's a saturated liquid. So on here, that's going to be our HF, 196.26. So we have everything we need for the hot fluid. We have both of these values, and we actually know the mass flow rate of the hot fluid. Now, so next we'll go to the cold fluid. Now, for the cold fluid is water, and the water is coming in at 70 degrees Fahrenheit, and we want it to not to exceed 77 going out. But remember, for water, and this is going to be the cold fluid, it's going to be delta H cold is going to be CP delta T like this. And so we need CP. And if we look in my book, this is table B6, and we're around 70 degrees. You can see CP is about 1, pretty much for all those values, around 70 to 80, so forth. So it's pretty easy. So 1 BTU per pound mass degree Fahrenheit. Then so we can put that into our equation up here. And I'll even wait and put it over here. So let's actually rewrite this equation down below. So this is going to be m dot hot h hot out minus h hot in. Again, this is all equal to 0 plus m c h c o c I like this equals 0. And now remember, again, for the cold fluids water, we're going to use this so we can replace what we have right here with our CP delta T. And now over here, let's substitute our values. And what was our flow rate for our steam was 50 pounds per minute. HOO is this. HHI is this. plus over here again, we had one. Oh, well, first of all, we have our MC dot. That's what we're actually looking for. And then we have our 1 BTU pound mass degree F. And then our delta T is going to be 7, huh? It's going to be this one minus that one. So the difference is going to be 7 degrees Fahrenheit, like this. And then, so let's solve for MC dot. So of course, over here, when the Fahrenheit cancel, we have BTUs per pound. So we have 7 BTUs per pound mass times MC dot. And if we bring this over the other side, on this side, this was negative 48,000. We bring it the way, it'll be a positive 48,000. And let's see, the pound mass will cancel. So we're going to have, let's see, yeah, we'll have BTUs per minute, like this. And then we solve for MC dot. And we divide this out. Let's see, the BTUs will cancel, so we'll end up with pounds per minute. And it's around 58.1 pounds per minute. Let's take a look at this problem. Saturated water vapor enters a heat exchanger at 25 psi with a flow rate of 100 pounds per minute, and it exits as a saturated mixture with a quality of 0.2. The steam is cooled by water that comes in at 68 degrees Fahrenheit with a flow rate of 10,000 pounds per minute. What is the exit temperature of the water? So maybe we have a picture something like this. We have saturated vapor entering at 25 psi and 100 pound mass per minute of the vapor. And it's exiting at 25 psi with a quality of 0.2. Obviously, it's saturated mixture when it exits. And again, this is the hot fluid. And the cold fluid is coming in at 68 degrees Fahrenheit and exiting at a temperature we don't know. Again, as we're doing this problem, keep the equation in mind that we need for heat exchangers. Keep this in mind. And again, it's best to maybe set up a little table for the hot fluid. And over here, maybe the cold fluid. And for the inlet for the hot fluid. And the outlet. And for the inlet, we know that that's saturated vapor at 25 psi. And we'll, again, since saturated vapor, again, that's going to be our hot, and that's going to be our inlet. So that's going to be HHI. And since it's saturated vapor, it's going to be equal to Hg, like this. So we'll look at our table at 25 psi and our Hg, which is 1160.7. Of course, that is BTUs per pound mass. And that's probably all we're going to need for that column. So then let's go to our hot fluid outlet. Let me move that outlet over a little bit more. And that's a saturated mixture, 25 psi. And what did we say our quality was 0.2? So that again, that's going to be our hot outlet. So it's going to be HHO. And of course, that's going to be our HF plus X times Hg minus HF. So if we look these up in our table, again at 25 psi, our HF is 208.52. Of course, our X is 0.2. And then we have Hg minus HF. Now, in my table, it gives that difference over here. That's called HFG, and that's 952.2. And put that in your calculator. I'm getting 398.96 BTUs per pound mass, like that. And I think that's all we need for the hot fluid. Now, for the cold fluid, once again, that's going to be water. So, for the cold fluid, our delta H cold is going to be our CP delta T. And once again, if you look it up in the table, in my book, it's table B6. If you look up for around the temperatures we're dealing with, 60 to 70, CP is always around, it's actually about 1 BTU per pound mass degree F. Like this. So let's put everything into our equation. So once again, we have this equation up here. And again, for this CO minus CI, we use just CP delta T. And again, we want to find the temperature. Remember, that's what we're looking for. So we might as well keep those separate because we're going to be solving for the temperature. So again, that's going to be, say, T, I'm going to call it that T out, excuse me, T cold out minus T cold in. like this, and then start substituting our values. And we know, and our flow rate is 100 pounds per minute for the mass flow rate for the hot. So that's what actually we need. And our H hot out was 398.96 minus our 1160.7. I'm going to put the units on the end here. And then the flow rate for the water was 10,000 pounds per minute. And then our T cold out is what we don't know. And I'm going to just, yeah, I'll distribute. Well, actually, first of all, I better put the CP in. So it's 1 BTU per pound mass degree F. And I'm going to multiply, I'm going to distribute all these over. So this will end up being our TC cold out. And then over here, our cold in was 68 degrees. So if we multiply uh, this over to that, let me multiply this out. When I do that, the pound mass will cancel. And so we'll end up with minus 10,000 BTUs per minute. T uh, cold, but we know what that is at 68. Like this. And that's all equal to 0. And multiply these through. So we multiply this out here, we get negative 76,174 BTUs per minute. And of course, over here, this is going to be 10,000 BTUs per minute times TCO. Over here, we get 680,000 BTUs per minute. And so if we combine these two here and divide through all the BTUs per minute and solve this, you end up with T cold out to be 75.6 degrees Fahrenheit, like that. So that's the exit temperature that we would have for this particular problem. When we're cooling the saturated vapor from this down to saturated mixture of 0.2, the temperature would go in at 68 and exit at a little bit over 75 degrees Fahrenheit. And that's what we want to know, what the exit temperature of the water was. I'll go through this heat exchanger example pretty quickly this time. It's very similar to the other one, just things are kind of rearranged a little bit differently. A saturated steam mixture with a quality of 0.8 enters a heat exchanger with 50,000 kilograms per hour, and the pressure is 10 kPa. Should probably better be pressure of. The steam exits the saturated liquid. The steam is cooled by water that enters at 20 degrees C and exits at 35 degrees C. What is the water flow rate? Again, we'll have a picture of something like this. We have our hot fluid going in. It's a saturated mixture at 10 kPa, and the quality is 0.8. That's, of course, going to be our X value. and it's exiting as a saturated liquid. Water is going at 20 degrees C and exiting at 35 degrees C. Again, I'm going to go through this much more quickly than the last ones, so you can slow things down or stop the video if you need to. Once again, keep in mind this equation we're going to use. Again, keep in mind we have an inlet 10 kPa, saturated mixture 0.8. And if you look in the table, in my book, it's table A11. Again, we have SI units this time. And to find, we need these values here. Now to find HHI, we'll have to use this because it's a saturated mixture. And look up HF plus 0.8 G minus HF. And that gives you HI of 2106 kilojoules per kilogram. And for the outlet, we have a saturated liquid. And in the table A11, again, saturated liquid HHO is HF, and that's 11.83 kilojoules per kilogram. And so then we know all of these values here because we know the flow rate, so we know everything here. And we're looking for this MC, so now we're going to work on this side over here. And again, for water, we're going to use delta H CP delta T. And if you look in the table A6, the values around, I'm going to use around 4.182. That may be a little bit off, but that's pretty close. And the difference, delta T, difference will be 35 minus 20. So that's going to be 15 degrees C difference, which again, remember the difference in absolute and Celsius is going to be the same. So that's a 15 degrees C difference, and that's the same as 15 degrees K difference. So if we calculate our delta HC, that's 62.73 kilojoules per kilogram. Again, you can stop or slow down the video if I'm going too fast. And again, looking back at our equation, we can now substitute our values into this. Again, this is our hot fluid, our cold fluid. Again, over here, this HCO minus HCI is this delta HC. And so substitute our values up here, 181.83, 2106, times our hot fluid flow rate, 50,000 kilograms per hour. And putting the 6273 in here and getting this, then go ahead and just solve everything for MC dot. And again, notice this is going to be a negative here. When we bring it to the other side, it will become positive. Then we'll divide by the 6273. And then the flow rate required is 1.5 million kilograms per hour. Or if you divide that by 360, it's 423 kilograms per second.